Gradient descent in machine learning, the engine of learning. Gradient descent is a fundamental optimization algorithm used to train machine learning models. It enables models to minimize errors and improvise predictions iteratively, powering over 90% of deep learning architectures of today. The core idea of the descending the error landscape. Imagine a blindfolded person walking downhill in search of a valley's lowest point. This is analogous to gradient descent, that is, relatable to gradient descent. The objective is to find the parameters, which are the weights and biases that minimize a cost or a loss function, which quantifies the model's error. It's an iterative process, taking small steps in the direction of the steepest descent until the lowest point is reached. The mathematics behind the descent. Theta nu is equal to theta old minus alpha delta j into theta. Theta. It is the model parameters. For example, the weights and biases of the descent gradient. Next, j theta, which is called the cost function. For example, the mean square error or the cross entropy that quantifies the model error. Delta j theta. It is the gradient of the cost function, indicating the direction of the steepest ascent. And alpha. Alpha is called the learning rate, a hyperparameter controlling step size. The typical values of the alpha in the descent are 0.01 and 0.001. How gradient descent works. A step-by-step process. Gradient descent can be broken down into 5 steps. Initialization, calculate gradient, update parameters, iterate, and convergence. Coming to the first step, initialization, means start with a random model parameter, for example, weight or a bias even. The second step is calculate gradient. Compute the gradient of the cost function with respect to current parameters. And then we have the third step, update parameters. Adjust parameters by moving in the opposite direction of the gradient. Scale by the learning rate. The fourth step is iterate. Iterate, the meaning of iterate is even repeat steps. So we have to repeat the steps 2 and 3 for a fixed number of iterations, epochs, or until convergence. The final step and the fifth step, convergence. Stop when the change in the cost function or parameters are below the threshold or the gradient is nearly zero. Types of gradient descents, efficiency and scalability trade-offs. We have three types of gradient descent. First one is the batch gradient descent, also known as BGD. The second one is stochastic gradient descent, which is SGD. And the third one is mini batch gradient descent, MBGD. The first one, batch gradient descent, BGD. The batch gradient descent uses all training data for each parameter update. It is comparatively slow for large datasets. Example 1 million plus samples, but guarantees convergence to global minimum for convex functions. The second type of gradient descent is stochastic gradient descent, SGD. The stochastic gradient descent uses one random training sample for each update. It is fast, but updates are noisy and may oscillate near the minimum. The third type and the last type is mini batch gradient descent, MBGD. The mini batch gradient descent uses a small batch. Example 32, 64 and 128 samples for each update. It balances speed of the SGD, the stochastic gradient descent, with the stability of batch gradient descent. Most commonly used in practice. That means, compared to three of the types, the mini batch gradient descent is most commonly used in the real life. Challenges and solutions in gradient descent. Local minima, learning rate selection, and vanishing and exploding gradients. Let us look into the local minima. Local minima. Gradient descent can get stuck in local minima in non-convex cost landscapes. The solution is random initializations, which are more advanced optimizers. Coming to learning rate selection. Too high causes overshooting. Too low results in slow convergence. What is the solution? Learning rate schedules, adaptive learning rates. And then the vanishing or exploding gradients. Gradients become extremely small or large in the deep networks. So what do? The solution is batch normalization or ReLU activation or gradient clipping. All these are solutions and the problems of gradient descent. Key applications across machine learning models. So we are here to learn about the gradient lesson applications in the learning models, machine learning models. First, we have linear regression. Linear regression is minimizing mean square error, MSE, for optimized line of fit. The second one is logistic regression. Logistic regression is used for binary classification, minimizing cross entropy loss. The third one is neural networks. Neural networks is the core of backpropagation for updating weights and biases. And then we have support vector machines. Support vector machines can be used for training using gradient descent for large data sets. And then last, we have recommender systems, optimizing similarity functions for recommendations. Real world example, predicting house prices. Let us see a scenario. Training a model to predict houses price Y based on size X. So here the house price is Y and the size of the house is X. In the model is Y slash pred is prediction is equal to M star X plus C. Here M and C are parameters. Cost function MSC is equal to 1 by N into Y prediction minus Y actual at the rate of 2. Process. Processes initialize random M and C. Iteratively adjust using gradient descent, reducing MSC from 50,000 to 1200 over 500 epochs with alpha is equal to 0.01. What is the result? The result is the model converges to M is equal to 250, C is equal to 50,000, reflecting optimal price and size relationship beyond basic gradient descent. Advanced optimizers. We have a list of advanced optimizers here. First one is momentum. Accelerates gradient descent in relevant directions by incorporating previous updates. Adagrad. Adagrad adapts learning rates for each parameter, smaller updates for frequent features. RMS prop addresses undergrads' decaying learning rates, performing well in non-convex settings. Adam combines benefits of momentum and RMS drop, often 2 to 5 times faster convergence than SGD. It is widely used. And we have Nesterov accelerated gradient, a variant of momentum that looks ahead before taking a small step, improving efficiency. Conclusion: the enduring importance of gradient descent. Gradient descent is the foundational algorithm for modern machine learning and deep learning. It is versatile, applicable across a wide array of models and problem types. With continuous evolution into more efficient optimizers like Adam, understanding gradient descent is crucial for anyone working with data driven decision making and AI systems.